So in this lesson, we're going to talk about a new data structure called priority queues. So we start with a simple question. What if there's a data structure that can always find min of a set efficiently? So that's an interesting question, because if you have an array which is not sorted, finding a min would require big O of n operations. So we don't consider that to be efficient. Now, if you have an array that is sorted, you can find the min in big O of 1. We consider that to be efficient. But keeping something sorted is a very big requirement, at very expensive. So we know even the best sorting algorithm requires n log n. So what do we think about a data structure that can always find the min of a set efficiently? Maybe perhaps in big O of log n or big O of 1. So let's think about that question. Now, before we get there, let's talk about the complexity of operations with the data structures we know. Now, it never hurts to revisit this table again and again, because it gets you to think about some of the most common operations you do, such as insertions, searching or finding, removing something, finding max and min. So in terms of an array, which is an arbitrary array, we know that inserting something to an array can be done in big O of 1. How do we do that? We just stick the element to the back of the array. Finding something in an unsorted array would require big O of n. It requires us to look through the entire array to find this. Removing something would require for you to look for it. That itself would cost you big O of n. But then you'll have to adjust the array to make sure that the hole is filled. And max and min, finding max and min in an unsorted array would require big O of n. Now, if you have a sorted array, you can do insertions, still would require big O of n now, since we have to maintain the invariant of sorted. And finding something in a sorted array using binary search can be done in log n time. Removing something in a sorted array would require big O of n, since we'll have to find it and we'll have to adjust the array to remove it and maintain the sorted invariant. Max and min, we know, is at the end of the array, so therefore you can find max and min in big O of 1. When it comes to linked list, you can insert something to a linked list, the front of the list in big O of 1. Finding would require you to traverse the list. Remove require you to traverse the list and remove it. And finding max or min will require you to look at all the elements in the list. So the complexity of operations go as O1, On, and so on. If you have a sorted linked list, it doesn't give you any advantage. In fact, you will have to maintain the sorted invariant after you insert. So that would require big O of n. You will have to navigate through the list and find the place and maintain the sorted invariant. Finding would require big O of n. Removing would require big O of n, since you'll have to look. And max or min would require find big O of n. Now, when it comes to stack, what we mean by insert means we push something into the stack. That is big O of 1. Finding means that you will have to look, if you're looking for any element in the stack, you will have to pop all the elements from the stack and then look for this element that would cost you big O of n and put the stack back into its original shape. Removing something from the stack only can be done from the top, which we call pop. So that's big O of 1. Max or min from a stack would again require you to look through the entire stack by popping elements and pushing them back into the original format. So that's big O of n. When it comes to queue, inserting means n-queuing elements, which is big O of 1. Finding something would require, similar to stacks, a big O of n operations. You'll have to dequeue, look at them, find this element, and you will have to put the queue back to the original shape. Removing is dequeuing the element, so that can be done in big O of 1. Finding max or min would be similar to finding any other element. We'll have to traverse through the entire queue to find it. When you have a hash set, we have very efficient way to insert, very efficient ways to find, very efficient ways to remove, but anything to do with the order statistics like max or min will cost you big O of n when it comes to the hash table, because in a hash table you will have to look through all the elements in the table to figure out which one is there. So for instance, if you have a hash table like this, you would look at all the chains in the hash table before you can determine which key is the largest key. Now typically, if you assume that the load factor of a hash table is 2, you would assume that if you have n elements in the n keys in the hash table and the hash table size is n over 2, since the load factor is 2, then it would require you to navigate to n over 2 chains. Within each one you're going to go no more than n operations. So what your complexity of operation, finding max or min in a hash table, is big O of m. Now, so this brings us to our original question. What if there's a data structure that can always find min of a set efficiently? If you look at all of these things that we discuss, the two things come to our mind about finding min efficiently. One thing actually, that you must have a sorted array to find max or min efficiently. Now this is a heavy requirement. Keeping an array sorted costs you n log n operations. So it's not always possible to keep something in a sorted manner. So what if you can keep something partially ordered? So let's think about that a little bit in a little bit after we talk about why we study such data structures. So to understand our concept of a queue or priority queue, we need to understand why we study priority queues. Let's take a regular queue where you do DQ from the front and NQ from the back. So let's assume that you have a grocery, you go to grocery store and you wait in the checkout counter, and there are people in front of you. Let's say the first person takes 20 minutes, second one 2 minutes, third one 10 minutes, the fourth one 5 minutes. So you ask the question, what would be the average time, average wait time per customer if you're waiting in this line, and assuming that there's no one else coming and joining this line. Now clearly, if you try to compute this, we don't know that the first customer will have to wait 20 minutes until that customer is served. The second customer will have to wait 22 minutes. First customer plus its own waiting serving time. The third customer will have to wait 32 minutes, that is 22 plus 10. The fourth customer will have to wait 32 plus 5, that is 37 minutes. So if you find the average, you divide this by 4. So let's just add them up. 7 plus 2 is 9, 11, 1, that's 3, 3, 6, 7, 9, 11. So we got 111 over 4. Now roughly this is about 27 minutes per customer. So that's what we get if you serve them in the order they come. Now let's think about a problem in a different way. Let's just assume that we always serve the smallest client first. Now the only thing I'm asking in this case is that the minimum client be at the front all the time. So there's no requirement for this to be any sort of in a sorted order. So that can be unsorted as long as I bring the next minimum to the front once that client is served. So you can think of this as in the grocery store, always the cashier says the person with the smallest amount of items come forward. And so that's what happens. After serving each person, the cashier will call the next person with the smallest amount of items. So let's just compute the same. We have the same numbers now. We have the same customers, but the customers are served based on the amount of items they are carrying. So if you look at the previous one, we had the same customers 22, 10, 5, we still have 20, 2, 5, 10, 20. All right. So now let's compute the average wait time. First customer is 2. The second customer is 2 plus 5. The third customer is 7 plus 10. The fourth customer is 17 plus 20. So we divide this by 4 to find the average. So if you find the average here, 37 plus 17 is 54, plus 7 is 61, plus 2 is 63. So we have 63 over 4. That's roughly about 15. All right. So now it's very clear then, looking at these two scenarios, that the FIFO queue does not perform quite well as opposed to a priority queue. So the first in first out seems to be the average time is really bad for all of them, as opposed to a priority queue where the average time is 15 compared to the first in first out where you had 27. So why is this scenario important? Let's think about some of the applications. Let's say there's a router. The router gets data packets. So you have data packets coming from various places, and you can decide to send data packets in the order they come. So there's a 2 gigabyte movie coming in first. You send that first. And then you have a 2 kilobyte text file coming next. So the text file will have to wait until the 2 gigabyte movie file is cleared. So if you change the order, it can help both perhaps. All right, so the idea is like in a routing situation, if you have a router, you can improve the serve time, average serve time for all of them by organizing them in a priority queue. So that's the idea. So the priority queues can be very efficient data structures for implementing several applications. So in terms of implementation wise, we can define an abstract interface for the priority queue, such as priority queue new. That will create a new priority queue, checking for empty priority queues, full priority queues, inserting something to a priority queue if it's not full, and finding the minimum in a priority queue or deleting the minimum in a priority queue. These are the only operations we are asking it to perform. So how do we do that? So let's think about priority queue invariant. So when you think about this, you're going to say, okay, I need a data structure such that this. The first thing that comes to your mind is that I can probably maintain elements in an array. Well, let's just say, for reasons that will be known later, that we are not going to use the first location in the array, the 0th location. So we assume that our priority queue invariant would be the minimum is always the first element in the array. Okay, so what we're going to say is that A's of 1 is always, that's our minimum, is less than or equal to A from 2 to n. Alright, so we are saying that for all elements from 2 to n minus 1, all those elements are either greater than or equal to A's of 1. Now in a priority queue, it's not necessary for the elements to be distinct. So even though you have the minimum here, you can have another element that is equal to the minimum in another place. Like for example, you can have minimum to be 2 here, but you could have another 2 here. But that 2 will come to the front once you delete the 2 you have in front. So the priority queue invariant is that we know that in this type of a situation, that we'll have A's of 1 is always less than or equal to the rest of the elements. And this is going to be useful for us to write our SPQ function. So if you have a priority queue called H, that we can have a Boolean function that checks whether it's a priority queue or not. So let's think about the naive implementation of a priority queue using just a simple array. Now for reasons that you will find out later, I'm not going to use the 0th location of the array. So I'm always going to assume that in my priority queue, the only invariant I need is that the minimum is the as of 1 element in the queue, priority queue. I do not care about the other elements. All the thing I know is that A1 is less than or equal to all the other elements from 2 to size minus 1. Now let's think about some of the complexity of operations when we do this. So let's say that you have a priority queue where you have a minimum element here, then the other elements are always greater than or equal to that minimum element, so you can have a 2 again. And so here's how your priority queue looks like. So if you try to insert something to the priority queue, so what you will need to do is, let's assume that we are inserting something that's strictly less than the current minimum. So what we need to do is to insert 1 into that location and put this element all the way back to here. So we'll take the current minimum to the end and then insert the element 1 into that location. So that seems like a simple operation to do that can be done in big O of 1. We don't shift anything, we just swap 2 elements, we write the as of 1. Now if it comes to delete min, let's see what happens. Now here's the original priority queue, and I like to delete the minimum from the list. Now after you delete the min, obviously in order to maintain the priority queue invariant, you must find the minimum from the rest of the array. So that's going to cost you big O of n operations to do it, since they're not ordered. So let's just say that we found this to be the next minimum element, and then you will have to somehow send it here. But I think rather than creating a hole here, what I would do is I will swap these 2 elements. So I put the 2 here and the 5 here, and then I swap these 2 elements here, and so the 2, this 2 will come here now. So that's a big O of 1 operations where I didn't have to adjust the array at all because I didn't create a hole. I just swapped the element with the back element and put the back element in the front. This is sort of similar to your pancake sort algorithm somewhat. Now find minimum, so this find minimum is a big O of 1 operation, so you can easily find the minimum means just returning as of 1. So find min can be done in big O of 1. So it seems like a simple array where you maintain the invariant that the minimum is at the front. Seems like a decent one, but except for the fact that delete min would cost you big O of n. And we don't like to do that, because if you perform many delete min operations, then the cost can be very expensive. In other words, if you perform delete min n times, you have an n squared algorithm which can run really slow for large n. So therefore big O of n delete min is not particularly appealing in terms of maintaining this queue. So in the next lecture we will talk about the more efficient data structure for implementing a priority queue.